and practical applications. So I'm not going to read his bio from here. All of you have seen that. But let me just tell you a couple of things about Xiaodong. He did his PhD at Berkeley in, I think, 1986. And then since then, he has been with Cornell University. Okay, so all these years. And he also started a company called Bigwood Systems, which actually commercializes some of these techniques that he's going to talk about, but even more than that, right? So the remarkable thing about Xiaodong is that he works the whole range of things that you think of a professor can work on, starting with the basic mathematical foundations of power systems, all the way to actually making things work on the real grid. All right. So, and he excels at both ends of the spectrum, which is, I don't think there's too many people who can claim that. So he has fundamental theorems that he proved about the dynamics of the power system, and which resulted in his working out how to do stability calculations without running step-by-step calculations of this, all the way. And then that technology is now running on a couple of dozen different power control centers around the world. Similarly, in the optimization space, he's done the same kind of thing. So as I said, there's very few academics, professors that can actually write the mathematical stuff on the one hand, and he's written more papers than almost anybody I know. And on the other hand, he's got his software, all his packages working on around the world at control centers. So with that, I'm going to let you tell us how you did that.
Thank you very much, Angel. Actually, I learned a lot from you over the past 2 or 3 decades. I enjoy our relationship a lot. And today, thank you very much for this invitation. And I'm going to share with you some of my knowledge on this optimal power flow technology. I will start from computation, and then theory, and then applications. Because my theory was inspired by interacting with the utility, and that I started to work on the theory of OPF. So when I was an assistant professor, I set up the route. I want to work from university to industry. So I divide into 6 stages. I want to do the theoretical foundation, because theoretical foundation will give you the belief that the approach you take is correct, give you the belief. And that's why from the early day, my work on the direct method, controlling UEP from 86, remain the same up to now, because I believe controlling UEP is the best. Okay. So from theory, and then I do solution methodology to solve the problem, and then numerical implementation is the different story from solution methodology. At the university, if my students say, Professor, this is a BCU diverges because Newton method diverge, I can accept. But at the company, if my engineer say, oh, this case because Newton method diverges, I will not accept. We need to implement a very reliable, robust numerical method based on your solution methodology. And then do the software implementation, industrial interaction, and then practical installation. All this require different kind of skills. But I'm lucky I have people help me, my engineers, colleagues, and then feedback to theoretical foundation. So over this, we have published about 480 papers and 30 patents, about 20 some is US patents. And now product is about 31 products over transmission and distribution and optimization. So I enjoy this route. And for example, the top one is California ISO Control Center. The bottom one is the PJM Control Center. And if you look at the California ISO, they have 3 groups of users. The green one is an operator. And the orange one is an online study mode by planning engineers. I should say operational planning engineers. And then the blue one is a look ahead, 2 hours, 4.5 hours, and day ahead study. Okay, so they have 3 groups of users. And in the control room, there are 3 basic functions are states mentioned every 1 minute, contingency analysis every 2 minutes, our package voltage stability and assessment every 4 minutes. So this is 24/7. Our package is to ensure voltage stability and calculate the transfer limit for each interface. They have about 20 some interfaces they define. We have to compute. It's a transfer limit. And the same thing at PJM. PJM adopt our technology in 2003. I think probably this is the first online VSA in the United States, 2003. And the California ISO is 2008. And I document some of the theory in the book, Stability Regions of Nonlinear Dynamical Systems, published by Cambridge University in 2015. Okay, so this is our key customers. So our product each must have a unique and innovative methodology in order to compete against large competitors. Otherwise, we have a little chance to get to winning the project. Okay, so optimal power flow. So I started this research in 2006 or 8, initiated by Tokyo Electric. At that time, they say, let's also work on OPF, optimal power flow. So as you know, OPF has been an active research and development area since 1962, right? 62 years, right? Over the last 62 years, from the first paper by Carpentier, right? So basically, you want to optimize an objective function subject to quality constraints, which is the AC power flow, and the equality constraint, which is a thermal limit, and voltage violation, a voltage constraint, transformer constraint, phase shifter constraint, capacitor constraint, real power and reactive power constraint. So this is a very generic representation of OPF. I work about 4 to 5 years with TEPCO on this topic, and I summarize the number of different objective functions. Actually, it's 53. Our typical one is a production cost, losses, right, blah, blah. But actually, there are 53 different objective functions depending on your application. Okay. And but according to FERC study, a robust ACOPF solution can potentially save $40 billion every year in 2022. So this is a FERC study by this gentleman. He just retired, Dick O'Neill. Dick O'Neill. Yeah. So we need a robust ACOPF. We need. So OPF competition started in 2018, right? Originally, the competition's first place, you have $2 million. Second place, 1 million. Third place, $500,000. Then later on, they revised 5 million to invite 20 teams, 20, each team $250,000. Then award 4 million. Second year award 2 million. So total is 11 million in the competition. And these 20 teams, they invited, you have to participate in the competition. You have to participate. So they have a real-time mode. You have to solve the problem in 5 minutes. And then offline mode, 60 minutes for each problem. Division 3 is you can consider line switching as a control. Real-time mode and the offline mode. And this is the final score. This slide is not, yeah, my slide here is different from this one. I don't know why. Yeah.
Oh, it's not, it's getting cut off.
Yeah.
Oh.
Okay. So, but it's okay. So Division 1, we are number 2. Division 2, actually our award is number 3 because benchmark doesn't count. Division 3, we are number 2. GOTBSI OPF. Division 4, we are number 3 because benchmark doesn't count. We are number 3. So this gentleman, he's quite good. Always number 1. Always number 1. But in last year competition, he was number 6. Yeah, but
This year he was.
Yeah, not so good. But now he used to work in a national lab because his performance. Right now he works for Groupie.
Now he will.
Groupie. Yeah, yeah. So yeah, he's quite strong, and we compete against Columbia, Addy, this team. And Pearl Street is from Carnegie Mellon, department head, this company. And at the bottom, we have a Sugar CMU, another team from Carnegie Mellon, Case Western Reserve, a consultant company, and Penn State up. But they all get 0 score, so I don't know why they.
So there's 2 Carnegie Mellon teams?
Yeah.
Gee.
In the first team, the bottom one is the team from Berkeley.
Okay.
Is this gentleman, Jabba.
Oh, yes.
Yeah, this team was the last one, Jabba. Okay, now I want to share with you the top 10 teams all use interior point method. Okay, the difference is how do you tailor your algorithm to OPF. So I'm going to show you how I improve interior point method by exploring the problem structure of OPF. And Angel, you have a paper in the past. You solve the DC and then improve catch on the reactive power part. Okay. Yeah, you publish in IEEE transaction. Yeah, that is one improvement. But I use different route. So very quick overview of interior point method. Right, you have an objective function, you have inequality constraint, you have inequality constraint. So first step is you convert this inequality constraint into equality. Right, so everything is qualitative. Right, you have this constraint, positive number. Second one is you eliminate this one by putting them as a penalty objective function. Right, and then you have equality. So you are solving equality constraint optimization problem, and now you use Lagrange. You form the Lagrange. You take the first order necessary condition, KKC conditions. So you need to solve this set of algebraic equations. And interior point method use a Newton method to solve it. Right. Okay. So if I use this pure interior point method by IBM, they have an open source. Maybe I will get outside top 10. No, I cannot get into top 10. So when I look at the problem, I realize the problem of interior point method. That is this number, thermal limit. One is nonlinear. Thermal limit is nonlinear. Second one is this number is huge. For power network, the most number of component is transmission line and the transformer. So interior point method, no matter what, they constrain yourself by consider this in advance. Right. All the inequality constraint into equality constraint, and then take the Lagrange. That's wrong. That's not the right thing to do for solving OPF. So the method I invent is the following. I want to still use interior point method, but I want to improve it. So I want to deal with this thermal limit. Particularly, I want to deal with it. So I give you an example, PJM case. Their system, number of buses, 13,183. But the transmission branch is 18,168. Right. And thermal limit is times 2 because both end. So the inequality constraint become 36,336 times 2. So you constrain yourself by 18 this one. So my approach is first, I neglect thermal limit. Neglect it. Okay. I solve a relaxed problem. And interior point method converge beautifully. And then, so if I neglect it without thermal limit, then my number of constraints here, the nonlinear equality is 0 because I neglect it. And no problem for interior point method to solve this very, very fast. And then I need to deal with it. Right. So once I get a solution for stage 2, I check the thermal limit violation. And for sure, it's not 36,336, right? It's less than 200. Less than 200. Right. Actually, it's less than 100. So I take the active set concept, violation, I take it back to deal with it. And then active set, 90% of violation, I bring it back to my problem. So my problem right now is only 200 nonlinear inequality constraint. Then I use homotopy concept to solve it. It's a little bit tricky how you can solve this faster. I use homotopy to increase the reliability. And then once I get a solution, I check again. Thermal limit violation until no violation. And then the last stage, I deal with a discrete value of transformer and capacitor. I deal with this one using sensitivity based. So this is basically my modification, okay, of an interior point method. And this one, I use a real-time, actually a state estimation result from PJM, about 5,600 megawatt loss, 2%, about 2%. Stage 2, stage 3, I can reduce losses about 45%. And then I want to check the robustness of my algorithm. So I use a continuation power block to generate 9 additional operating points until north point, until the end north point. And then each point I apply algorithm to see whether I can solve. So 10 out of 10, we can solve the problem. If I don't do this way, just use pure interior point method, only converge here up to here, 40% convergence. If I don't deal with it, this treatment. So this is if I use a one-stage scheme like a original interior point method, successful rate is 40%. And my proposed method is 100%. And we have a pattern in this one. And we also conduct convergence analysis. Right? I want to prove the convergence of my algorithm. I use my paper with my postdoctor on the global convergence of a class of homotopy method for nonlinear circuit system. So this is a general theory for homotopy method, and it's general for circuits and systems. We apply the theorem to prove our global convergence. Okay. Okay. Now, so I was excited about this one. So I called California ISO, said, send me a case. Let me try our algorithm. So they did send me a case, 6,500 plus. So about half of California ISO. California ISO is about half of PJM at that time. And I thought this can be a piece of cake, right? Smaller system. But turns out it's a piece of iron. I cannot solve it. I cannot solve for 3 months. Then what would you do? So I couldn't remember how many meetings I have with my engineers. What's going on? We couldn't solve it. So I was also very quiet. I didn't call California. Very quiet. And one day when I was driving in May, I remember that May, I realized there's no solution. Right? I realized there should be no solution. But you cannot say no solution. You have to prove it, right? You have to prove. So that is the second story. I went through a lot of proof. Okay, it's this paper, feasible region of optimal power flow, characterization and application. This paper. So this paper gives you a complete characterization of feasible region of OPF. If the feasible region is empty set, then there's no solution. And this empty set, this theorem says if empty set, then it will also converge to degenerate stable equilibrium manifold. And that degenerate information, which is one vector, will tell you why there's no solution. Give you a physical explanation. So I think here, I like this result. And that's why I want to share with you. This can be a useful tool for your research. So what happens is this. You have an equality constraint. Nonlinear power flow. You have a nonlinear inequality constraint, thermal limit and others. So whether the solution exists, that is whether there exists a set of control satisfy this. So you identify the control. Okay, I want to use a generator rescheduling. I want to use a load shedding. I want to use a terminal voltage. You select your control. Select it. Then we do the next. Okay, I use this technique, slack variable, to convert your inequality constraint and equality constraint into equality constraint. Right. That is a slack variables concept. So we define feasible region is the collection of control variables such that H, which is control variable, state variable, slack variables equals 0. But you want to find U satisfy equality constraint and inequality constraint. So that is a feasible region. Now the question is, how do you characterize this feasible region? Give a complete characterization. And I look at literature. There are few work, only one from Canada, Met department, but they use the approach is very complicated, and I decided not to use that approach. So I developed my own. Yes, any question? Okay. So this is my approach. My DNA is dynamical system, right? So I want to convert the problem into a dynamical system problem. Your H, right? Hx equals 0. Your H, Jacobian H transpose minus I construct a dynamical system. I construct a dynamical system I call QGS. I want to use this dynamical system to characterize feasible region. And this is good for large-scale system. Large-scale system. Scalability is quite good. So I was able to prove a path connect set is a feasible component of constraint set if and only if it is a regular stable equilibrium manifold of the QGS of the dynamical system. So feasible region is the union of regular stable equilibrium manifold of the QGS. So for example, I give you an example. This 9-bus system. If you use a brute force approach to plot the feasible region is the left-hand side. You use brute force approach. You use my theorem, is the right-hand side, 1-to-1. This is a stable equilibrium manifold, regular stable equilibrium manifold of QGS. It's the your feasible component. So this feasible region has 3 components. Each component contains at least 1 local minimum. If you have a KKT point here, then you can have 2. If you have 2 KKT, you can have 3. So I published a paper, the lower bound of a local optimal solution. But there are some interesting theory. And this one is degenerate. This is a red one, degenerate stable equilibrium manifold. So if you increase the load, these two will bifurcate through this point. Then the feasible component from 3 to 2, and then from 2 to 1. And then this one will shrink when you increase the loading condition. And then at your limit operating point, it's a 1 point regular and then disappear. There's no feasible region. So it's from lighted loading condition. You don't have feasible region because of voltage constraint. And then when you use increased loading condition, bifurcation occur. You have 1 feasible component, and then 2, and then 3, and then 2, and then 1, and then disappear. I have a student work on this bifurcation of a feasible component. Okay, so this theorem say the feasible region is a union of regular stable equilibrium manifold of my QGS system. And then I was able to prove every trajectory must converge of my QGS system. Converge to one of the stable equilibrium manifold. But this stable equilibrium manifold can be regular, can be degenerate. But all converges. Okay, and then, this is the same, every trajectory converges. So what that means is any point will converge to a feasible component. Every point here converge to this feasible. So it's a global convergence. So this has a very nice property, global convergence, and this is a smooth manifold. Unlike Newton metal, Newton metal has a lot of hole here, divergence region. But this, we don't have that problem. Very smooth manifold. So as I said, this is a feasible region of optimal power flow. Is the first paper to characterize this feasible region. And then after that, we are able to prove OPF solution existence was a if and only if condition. Because California ISO that case, right, I want to come up with the condition under which OPF solution exists. And I give if and only if condition. And I give a lower bound for the number of OPF solution. As a lower bound. And of course, we can get the upper bound. But I think lower bound is more informative. And then this year, or end of last year, we come up with the if and only if condition. So you compute a solution, and we want to make sure this is a OPF solution, give you a if and only if condition. So necessary and sufficient condition. And then this year, I prove, actually this paper, the title is buy one, get two free theorem. Buy one, get two free. And all the reviewers say, good, publish. But the associate editor say, under one condition, I will accept. Change the title. I dispute. I say, do you remember there's a very famous paper called no free lunch theorem? But no free lunch theorem in optimization. And if that journal can accept, that's a first tier journal. And why we are also first tier? We should accept this buy one, get two free theorem. So that's why I was forced to change the title. The idea is this: if you compute your OPF using interior point method, and the interior point method can give you just a KKT solution, but not local optimal. It's a feasible solution, but it's not local optimal solution. And in this case, I encourage you, say, don't worry. You buy one, I give you two. I prove nearby there exist two local minima. And you can get these two local minima very easily. So you just move along the unstable manifold. So this I spend my time, I use 8 theorem to prove this theorem, to conclude one theorem. So generically, it's a buy one, get two free. Exceptionally, it's buy one, get one free. So I characterize condition under which is a buy one, get one free.
But you kept it in the abstract, huh? That was in your abstract.
Yeah, buy one, get two.
That statement of buy one, get one free.
Oh, yeah.
You kept it in the abstract.
Yeah,
That's good.
Yeah.
That's a buy one, get two.
So you have policy, I have a strategy. So we are very lucky. We get the best paper award in IEEE transaction power system. It's exploring this idea, QGS. It's a 2-time scale approach to characterize a steady state security region for the electricity and gas integrated energy system. So even though you have 2-time scale dynamical system, it can still characterize it's your feasible region. Yeah. So then we continue to compete against at the challenge 3, that is a unit commitment. Last year. So this unit commitment, if you look at the website, it said this will impact $400 billion market in this EIA report. So unit commitment, this is the goal of my company's product. Is you want to, given load, given a bunch of information, you want to determine each hour what is your commit power and what is the optimal dispatch within this one. So you will get this kind of curve in the unit commitment. So this time there are 15 teams, 15, and we get the first award. We get the first place in the event 1, third place event 2, first place again in the third event, and the last one we get to top 1, and top 2. So this is our performance in this competition. So this problem formulation is very complicated. It's a 320 equations, 320 equations. Your model cover very detailed. Right. It's so I don't. You can look up on the internet the model. It's a 62 pages problem formulation. The explanation of problem formulation is 62 pages. So they have 3 divisions. Division 1 is 8 hours, look ahead. So it's about 18 period because 8 hours look ahead. The first one is a 15 minutes for 2 hours, and then half hour for the next few hours. So total is 18 periods. This is division 1. Division 2 is 2 days unit commitment. Division 3 is 1 week, 168 hours. So 3 divisions. As I said, with division 1, we are number 1. Division 2, we are number 1. Division 3, we are number 2. So it's a very challenge because you have millions of discrete variables and constraints. And I found that the most challenging part is the ramping constraint. Ramping constraint is not easy. You want to optimize, you want to maintain ramping constraint. It's not easy. So this part, I pay attention to how to make sure ramping constraints satisfy. And they have a huge number of contingencies. So here, and their accuracy is very challenging. 10 to the minus 8 is a convergence guideline, not minus 5 or minus 6, minus 8. Right. So this part is very challenging. The convergence is a guideline is very tough. So 15 teams participate in the competition. And DOE support 10. And the other 5 teams, they just participate, fighting for this award. So this 10, the final score is 5 in the top 5, 5 in the bottom 5, the other in the middle 5. So the bottom 5, I don't know why. They have a good relationship or what, I don't know. The top 5, I think, based on their technique, right? So our score is very close to ensemble. Ensemble is the high score, then sum them up. Our score is very close to the ensemble. Our score is very close to ensemble. So I was very pleased with this result. And this is Division 3. We were number 2, next to MIT. MIT number 1. But our speed is the fastest. So 48.4%, we finished the first in the execution. So fast and nice result and very robust. We are the only team finish all of 630 test systems. Never fail. These 2, they finish 2, fail 628. So you can see it's quite challenging to solve the problem. But some team they did very poorly. Right. Okay, so here I don't have time to share with you how I make sure the ramping constraint in solving this ACUC. Right now, this area is quite, GE cannot produce ACUC, period. Okay. Some utility, some vendor, they claim they can solve UCAC, ACUC, that is not true. Like New York ISO, they use DCUC and then patch with the AC power flow solution. Patch it. It's not the ACUC. So even the largest vendor in the world, Texas, right? Australia, yeah, that company that dominate this market, they only produce DC UC. they cannot solve SUC. And Taiwan Power Company has a 7 license on this Praxis. But Praxis was acquired by a investment group, acquired by this investment group. And after this acquisition, they doubled their license fee. From each license per year is 100,000, they doubled to 200,000. But still, Taiwan need to pay this 200,000. So I want to share with you the practical application. So I and Hitachi, we signed a contract in 2013 to develop a system called OpenVQ, Smart OpenVQ. The objective functions are enable high penetration of renewable energy. That's number 1. Number 2, increase power transfer capability. Power transfer capability, that's the second objective function. The third objective function is CO2 emission, reduce. The fourth objective function is improve voltage profile and enhance voltage stability. So this one, we test on TEPCO case, the result is quite good. Even for loss reduction per year, their savings of 15 million to 20 million per year. Both ATC improved by 10% without smart wire. Without smart wire, we can increase the ATC by 10%. And then the impact on the CAPEX. But I want to share with you is another successful story. News release is 2023, April 26th. This is demonstration project. Is by NATO, supported by NATO. NATO provide $8 million for this demonstration project. So this is a group of people, engineer. And then at the ceremony, the ambassador from Japan, ambassador to Thailand, this ambassador and the governor, they joined the ceremony. And the OpenVQ become full automatic since November 2023. So it's a cross loop application from manual mode to cross loop. So it's running every 5 minutes at the control center. Yeah. And I was pleased, but majority of the work is by Hitachi. Hitachi, they license my Super OPF into their platform. And we do this Super OPF and voltage stability engine.
Which control center?
It's in EGAT, in Thailand.
Thailand.
Thailand,
yeah.
EGAT, yeah. So this is a hardware. And terminal, they look at the terminal. So this is district EMS system, not a national. And this is some hardware involved team. So SCADA communication interface with the, and then go to control room. We open VQ here, and then every 1 hour we issue control. Every 1 hour we issue control action, and then do the control. It will be interesting that we can have a demonstration project in this country. Yeah, so this is a benefits certified by third party. So if you say my CO2 reduction is this one, this should come from third party, not from your report.
Yeah.
Yeah, loss reduction from third party, not from your report. Cost benefit from third party, not your report. So we have 11 benefits. So this is a pattern technology we develop. Okay. Hey. So this is the last one. Okay. So that cover one practical application of OPF.
Thank you.
Yeah.
Questions?
You want to go online, people check.
Oh, let's see. Anybody online that wants to ask a question? We'll go here. Yeah.
Thank you for the presentation. I always learn a lot from your papers and of course from the presentation. My question is, can you maybe talk about what are some of the outstanding problems if you think about optimal power flow? Folks have been working for decades on optimal power flow and its applications, right? What in your opinion are some of the challenges that we are seeing, just from the fundamentals as well as from new concerns that are coming from, let's say, renewable integration of methods?
OPF has been an analytical tool. Some utility adopt in the system planning department. And recently, is because of power market, is a marginal LNP. But I think important one, the fundamental is the model is not correct. So before my retirement, I will publish a paper say this model is not good. Model is not good. We should use QSS. You know QSS? Why?
Yeah.
OPF supposed to move the control from one location to another location. Right? So there are two issues. One is about the dynamics. Right. Power system is dynamical system. Right. What's the dynamics behind this one? The second one is how can you ensure your system will converge to your optimal solution? Right. What's the dynamics behind it? 2 years ago, I published a paper. I challenged the contingency analysis using AC power flow. I gave a counterexample in the contingency analysis. Contingency analysis, again, is a dynamic problem, but we use static problem to approximate the solution. I gave a counterexample. Say contingency analysis, say the final steady state is this one, but I use my time domain, right? I converge to different one. And the different one has a violation and this one has no violation, etc. So my proposal, this is based on my PhD student, Wang. Right now he's a professor at McGill University. She's an associate professor at McGill. So in her thesis, we propose this QSS model and then prove its omega limit set is the same as time domain omega limit set. So accuracy, no problem. Computationally, time domain and the power flow is about 1 to 10 or 1 to 20 speed. And our solution is in the middle. It's maybe power flow is 1, we are 7, and the time domain is 20. So I think in the OPF, we should use this model. A very easy counterexample is we get a time domain OPF, and then we run time domain. and then discover there was violation. So this is fundamentally, I was not comfortable with the model. But in this area, I just don't want to bring this issue up yet. Because right now the model we can handle easily, very easy. That's number one. Number two is the control variable usually typically is too many. So operator, they don't want to implement. They don't want to implement. In my PJM case, I show beautifully we can reduce loss 45%. But I didn't tell you I need 2,000 control variables. 2,000 is a number. It's a large number of control variables. So a good one, like now in the control center, when we design corrective control, we just let the operator select the type of control. No cost control, low cost control, and high cost control. They select. So this shrink the domain of search space. And then we don't do pure because pure OPF is just also is not very. I just use a mix OPF and some domain knowledge. For example, to increase low margin, I will use data point bifurcation theorem, the left eigenvector, to select control variables. And then use this limit number of control variable, I apply OPF.
Other questions?
So in the project with Hitachi, you mentioned 4 objective functions. I think voltage stability, CO2 reduction, maximum energy transfer, I think PDRs and integration also. So do all these 4 objective functions, do they have the same weight, or are the weights based on how you listed them? Sorry.
Okay, so I have actually my architecture, I did not show it here. It's once an hour. I maximize the power transfer capability and every 1 hour. And there I identify the pilot buses with the voltage magnitude information. Say if the next 1 hour, if you can keep your voltage, these buses, their voltage at this magnitude, then you can ensure voltage stability and also increase the transfer capability. And then they broadcast this hourly information to regional control center. So regional control center receive this information. They put the pilot buses and the voltage constraint as a constraint, voltage magnitude constraint. They use their own local resources to obey this constraint, and then they themselves minimize losses of their own. So that is achievement of another objective function, like losses. And then once every minute, they send because this OPF will determine transformer tap position, capacitor position, and terminal voltage at generator. Then the terminal voltage generator substation information, then we use a minute scale. We check whether they obey this information, terminal voltage. So this a hierarchical implementation, and with the different objective functions satisfied at each hierarchical.
No one has a question. I don't want to hold.
I had a quick question. If you if your solution converges, or I mean, when it converges, will it ever converge close to the boundary of stability? So like, is the optimal solution ever close to the boundary of being stable and unstable?
That's a good question. And unfortunately, this one, transient stability constraints or voltage stability constraint is not considered in the common OPFs research.
Mhm.
And my former PhD student, we have shown that transient stability constraints cannot have an analytical expression. No analytical expression. Analytical. So you can now say, I consider this constraint, then transient stability constraint is taken care of. No. So that raised the question about the current work on OPF with the transient stability constraint. They always come up with the analytical expression, say, if I satisfy this constraint, I don't have. And we show that, no, it's impossible to have an analytical expression. So what is our solution? Our solution is we use BCU, work on BCU in the OPF to ensure transient stability.
Because I was wondering, since you based on the last answer, if you're giving an area general constraints you have to control within this area, if they were to accidentally violate that because they just made mistakes somehow, but optimal was close to diverging, then I was just wondering what that looks like. But I see that. Yeah. Thank you.
Can I have a follow-up question on what you said about model being incorrect in OPF? You're kind of saying that the boundary between quasi-static simulations and the time series models is not something that truly represents the real world or the actual system, right? My question is that with the integration of, let's say, inverter-based resources, is that boundary getting more blurred? Do we have to pay more attention to kind of, thinking about not separating out quasi-static with the time series simulations here, or what do you think?
It's a quasi-steady state, actually, depending on your intention, your intended application, because we have shown the omega limit set close to each other, epsilon close to each other. So time domain will converge to a solution, one solution, and the QSS will converge to the same solution. Yeah. But the trajectory itself is not correct. It's not close to each other. Yeah.
So does it get, are those, convergence results valid across different types of, resources that you have at the transmission level with different dynamics and only machine-based resources?
Okay, of course, in our theory, we have a theorem stating this omega limit set, and that there we have three, I think we call 3 or 4 conditions, like a consistency of stability region, because you have a fast system and slow system. Right. So when your fast system settle down, that stability region and the original stability region, what's their relationship? So we do have, I don't recall that 3 conditions. Yeah.
Just curious.
But you can, that paper is around 2015 or 2016 in power system. Oh, no, in circuit system.
Thank you.
Yeah.
What is your comment on I see that there are several factors over there, such as the computation time and other factors. So I guess that over time, as we have more processing power, probably computational time shouldn't be that much of the factor rather than enforcing convergence, enforcing the feasibility.
We are on the same page.
Oh,
yeah, we are on the same page. And that's why in my work, speed is the final stage of improvement. Yeah. But if you recall, in 1985, Quebec purchased supercomputer. So we always say, oh, we have a sufficient computing power. But as a matter of fact, we have more demand, right? More constraints to consider. Right? So either hardware approach to speed up or methodology to speed up, all important. Like PGM right now, they run the state machine every 30 seconds.
But what do they do with it every 30 seconds?
I don't know about PGM case, why they do it with it. But California ISO is they fit this state machine into CA contingency analysis, which is running every 2 minutes. So, but every 1 minute, what they do with it, in addition to real-time power flow, I don't know. Yeah.
So I was going to ask the same type of question. You know, some of your presentation was about the OPF solution itself, you know, how you speed it up and how it works. But I think you also said that it depends on the application. What are you going to use it for? You know, not everything requires very fast. For example, when you say the unit commitment, that's an offline situation. It's not dealing with real-time conditions at all. So, so you have some flexibility of time, or being able to run it on the cloud or run it somewhere else. So you want. So what are, I mean, going back to what Anamika was asking, what are the hardest problems right now? I mean, you know, the general thinking is that if you're going to use optimal power flow in real time operations, you know, that's probably where the hardest problem is. But I'm not sure that's the case.
Yeah. Actually, all my work with the power industry in the last 2 years all indicate that the unit commitment is important. But the unit commitment problem of the future is very different from what we are doing right now. The unit commitment in the near future is commitment of energy storage, commitment of renewable energy, commitment of conventional generator, these three.
Right.
And these three, you know, on top of this, because of reduced machine inertia, right? Then to deal with this is not just unit commitment. You have to make sure frequency response, transient stability is ensured. So this is a very hard problem, very difficult problem. Right.
And in practice, nobody uses an unit commitment with OPF. Like you said, the best they do is DC OPF with the unit commitment, because you're running maybe certainly 24 hours, but maybe even a week. So it gets stuck. And then the AC OPF with unit commitment is, I don't think anybody is doing it in practice, right?
GE, I have a contact with GE. Their market share, I think, is the largest one around the world.
On unit commitment.
On unit commitment.
Yeah.
They only have a DC.
Yeah.
But he said a customer from international customer, they require voltage information, voltage service over. So he think upper management team, he think GE needs to do the SUC in the near future. And Taiwan Power Company just will announce the bid maybe end of this month. There is a stages, ECUC first, then ACUC second. They still want to use ACUC.
So how much, what is the reason for doing is this for 24 hours? You're doing next day for UC? Is that the time frame?
Okay. Usually it's 7 days.
It is 7 days. Yeah.
Yeah. And 7 days, we have our package in the competition for 4,200 buses, 1,000 contingencies. I forgot the period. It's 2 days. Our DCUC on our machine in the shop is 29 seconds.
How big? How many?
4,200 buses, 500 generators, 1,500 dispatchable load.
Okay.
Yeah. So literature, you have 2,000 generators. Yeah. So our DC, we did a live demonstration to Japan. It's the 29 seconds we can finish ECUC. For ACUC, we need 173 seconds. Yeah, still very fast.
Yeah,
Yeah.
that's not.
Yeah, that's why in the competition we are fastest. Yeah.
Better than
Yeah.
anybody else. So let me. I mean, unit commitment, like you said, not too many people, nobody's using ACO. How many people are using ACOPF for market clearing?
You know, this country is all DC.
It's all DC.
All DC.
Even New York is DC.
Oh, New York is DC and then patch.
Oh, then patch the AC.
Yeah.
Afterward. Yeah.
So,
Okay.
and this Daniel Hutchinson,
Yeah.
he sent me an email. He said there are 4 reasons why PC is used. First one is only one solution, so there is no dispute.
No, right.
No dispute which solution you want to calculate your LMP. Right, that's the number one. Number 2, there's robust solver to solve DC.
Yeah.
Right.
It always solves.
Always solve. And then fast.
It's always wrong, but it always
Always
solves.
wrong. Yeah. And then it's very fast. Right.
Right.
Yeah. And the number 4 is easy to understand.
Yeah, but you see, my thinking is that for markets, see, the people who care about it don't care about the answer. They care only about the calculation of the money.
Yeah.
Right?
Yeah.
And so as long as you can calculate the money part and everybody agrees on the process, then it doesn't matter. And you know, as far as the market is concerned, you've got an answer. They give you the schedules and the costs and the clearance prices and all of that, and that's all you need. But they never ask the question, which is what you were asking: how feasible is the solution? You see, they think that's the operator's problem. If it's not feasible, you figure it out. Right? And this is what is happening even worse now with this for 22, because there is no model even of the distribution system in the market solution, right? So nobody's caring about feasibility. So I think they'll get by with the market that way, but you can't schedule your operations without doing the AC, without doing the rest of the due diligence, because you'll get into a problem.
Yeah, I agree. Yeah. So AC, we have to solve AC problem.
Yeah.
Yeah. And the more interesting. Yeah.
I think we'll call it a day today. Yes, thank you very much. Yeah.
Thank you.
Thank you. That are on the system. We'll shut it off now.
Yeah.